Now we are going to start operating system. So basically, what is operating system? It is an interface between user and hardware. For example, we have this operating system. So here we have our application and user, and it is hardware. So operating system, it works as a layer between user and hardware, so that user can interact with the hardware. It cannot directly interact with the hardware, so it will require an operating system to work with hardware. And what we have in operating system is, it is a program, okay, which is stored in RAM, and it works with CPU runs the OS program. So coming to the next topic, types of operating system. First is unit programming. What is unit programming is, it has only one program in main memory, okay, and we will also learn about multi-programming and multitasking OS. So what is unit programming? It allows only one program in memory at a time. It cannot have any other program other than the program executing in the memory. And because it can only execute one program at a time, so it will be a improper utilization of CPU. Multi-programming. It allows multiple programs to be in main memory, and we have is degree of multi-programming, which is called DOM. So number of processes in main memory is the degree of multi-programming. As DOM increases, CPU utilization also increases, but up to a certain level. It cannot surpass a certain level, okay. As more number of processes are in CPU, CPU utilization will increase. If less number of processes are there, then CPU utilization will be less, but it can work up to a certain level. Types of multi-programming. We have non-preemptive and preemptive. So a preemptive is a running process which can be taken out of CPU forcefully, and non-preemption is a running process cannot be taken out CPU forcefully. It cannot be taken out CPU forcefully based on the priority of other processes that we have in our memory. Third is multitasking OS, which is time sharing. So extension of multi-program OS, it is the extension of multi-programming is multitasking, in which we execute in round robin manner. Yani it means we will give a certain time bound for a particular process, okay, and it goes in concurrent execution in a sequence. System call. It is a way of programs to interact with operating system. So we have user process executing, call system call, return from system call. At that time we have mode bit is 1, and then we have kernel mode. So it is a dual mode of operation to protect process, which is a program under execution. And what program is? It is a set of instructions that we write. It's kind of an algorithm or a program that we are using to solve a particular problem. So what is a process? Is program plus runtime activity. For here we have operating system. This is our main memory. We have an operating system, and some other programs that are stored in the main memory. Okay, so for example, for particular one process P1, we have a stack, heap, data section, and code section. What a code section is have stored in instructions that are written in the program. Data section, it will store the static and global variables that are in a program. If we have some dynamic memory allocation, that will be stored in a heap. And stack, it will store local variable, return address, function parameters. So this stack, heap, and data section, this combined is a running state of a program. And what we have, the attribute of a process. So every process is have some attributes, which is a PID, process ID, PC, program counter, GPI, general purpose register, list of devices types, size, memory limits, priority state, and list of files. So basically it is stores them all in a data structure PCB, process control block for each process. It means our main memory will have a PCB block. So what PCB block will have all these data in the PCB block, right? So these all data for each block will be stored in main memory along with the OS. Okay, PCB for process P1, for P2. If we have other processes, then also PCB for all the processes will be stored in the main memory. After that, context and context switching. So basically, content of PCB of a process are collectively known as context of that process. Okay, these all information are called the context of a process that are stored in the PCB block. Okay, so here we are. Suppose we have a process P1 and P2. So if CPU is running process P1, so it will take in the process PCB of P2 and return the context of process P1. Switching the context means registers value. What we have the registers value in the CPU, those values will be switched. Okay, registers value of P1 will go out from the CPU, and register value of P2 that is going to be execute next will come in the CPU. So who does this work? Dispatcher does this work. It does context switching. We have next is process states. One is new. So what we have in new is all the new processes that are stored in a main memory will be in a new state, and when they are ready, they'll be admitted to the ready state. Okay, and scheduler dispatch. After this, it comes to running state, and if they are completed, then they'll be terminated. And if somehow another process P2 have the higher priority and it wants to go to the running state, then P1 will come to the ready state and P2 will go to the running state. And suppose if we are in a running state, but our process P2 wants to wants to have any input through mouse, keyboard or anything, then it will go and wait for IO event or any other process. So it will be in a waiting state or a blocked state. And after that, if the IO event completed, then it will go back to the ready state. And if non-preemption, there will be a no running to ready state. Okay, if it comes in the preemption, but if it is non-preempted, then this curve will not come here, because no preemption now, definitely. And types of schedulers: long-term scheduler, short-term scheduler, and mid-term scheduler. So what a long-term scheduler do is it schedules the process from new to ready state. So basically it schedules the process from new to ready state which are going to be executed next. Short-term scheduler, it selects one of the ready process to run next on the CPU. Suppose we have a list of process P1, P2, P3. Okay, so what short-term scheduler do is select one of the P1, P2 and P3 based on the priority or any other parameters that are assigned to the processes. So it selects one of the ready process to run next on the CPU. STS, short-term scheduler, only selects but dispatcher takes to the CPU. So what does it only selects, but who is going to take it to the CPU to execute this? Dispatcher will take it. Mid-term scheduler, medium term, it performs swapping, selecting which one to swap in and out. Okay, suppose if we are currently having P1 process in a memory, so which is going to be execute, so it performs swap in and out based on the requirement. Updated process starts. So we already know new, ready, running, waiting and terminate these states. But after this, medium term scheduler, we have this suspended ready and suspended block, two new states here. So if we are in the waiting state, so if any process is suspended, it will come to the suspended, and if it will get resumed, it will go back to the waiting state. And if process in ready state and is get suspended, it will get into the suspended ready state, and if it will resume, it will go back to the ready state. Once the process in suspended state, and if IO completion during the suspension, it will go back to the suspension ready state. Okay, what these two states are done by mid-term scheduler. After the scheduling queue, we have a job queue, ready queue, device queue. So all new states process are stored in the job queue. All ready state processes are stored in the ready queue. Process waiting for IO device for each device that will be stored in the device queue. It can be multiple based on the devices that we are having for input output. Okay, printer will have a different queue, disk will have a different queue. If we have mouse, it will have a different queue for each process. It can have multiple queues, but in job queue and ready queue we will have only single queue. There is a question: which of the following scheduler reduces the degree of multiple programming? First option is short term, long term, and mid term both. So what short term is, it only selects, so it cannot reduce or increase the degree of multi-programming. Long term only increase because it is bringing new process in the queue. Mid term can increase or decrease both, because we have already studied here like what it does, perform swapping of programs, like which is going to be selected. So it can also increase and decrease both. So answer is mid-term. Long-term scheduler controls the degree of multi-programming. It means it is increasing the degree of multi-programming, because suppose we have in the queue we have only process P1 and P2. What then we will have the degree is 2. If we have one other program in the queue, then we will have degree of multi-programming is 3. So this is how the number of programs that we will have in the queue, it is the degree of multi-programming.